This is a problem where we're interested in the concept of energy balance on a chemical reactor. So we have an adiabatic reactor, a simple A goes to B reaction, and the conversion is 50% in the reactor. And the notation we're using, H is enthalpy, and this is enthalpy per mole. So the question is, which one of these answers is the correct energy balance for this adiabatic reactor? So because this is a steady state reactor, then any derivative with respect to time, the energy balance is 0. There's no work in the reactor, it's just a plug flow reactor. There's no heat transfer because it's adiabatic. So the only terms left are the energy flow in the form of enthalpy and the energy flow out. So our energy balance really reduces to the enthalpy in equals the enthalpy out. And to be general, we would talk about the total enthalpy. But then we can take a basis of 1 mole of A entering the reactor. And the enthalpy into this reactor then would just be the enthalpy of A per mole. And at the inlet conditions, whatever temperature is coming into reactor. The enthalpy leaving then, since it's 50% conversion, we have a half a mole of A leaving, but it's at the outlet conditions, different temperature, and we have a half a mole of B leaving, again at the outlet conditions. This is then, because it's 50% conversion, this is the complete energy balance for this system. Enthalpy of A in is equal enthalpy of A out at the outlet conditions times 0.5 and plus the enthalpy of B out outlet conditions. Remember, this is kilojoules per mole, for example, times 0.5. So this means the correct answer is D for this system. And the question arises is, how did we account for the heat of reaction in this type of energy balance? And the easiest way to understand that is to look at some more specific numbers. So let's suppose that A comes in at 50 degrees C. And let's assume that A and B leave at 300 degrees C. So that happens to be the adiabatic temperature we'd get from the reaction. And so the enthalpy of A in is the enthalpy of A at 50 degrees C. Enthalpy of A out is the enthalpy of A at 300 degrees C, which we could write as the enthalpy of A at 50 degrees C plus the heat capacity of A times the temperature difference, 300 minus 50. And we could do the same thing for B. So I've written this for B also, and then we're just going to substitute back into the first law for this specific example. Enthalpy of A at 50 degrees C is what's entering our reactor, and then we have 0.5 enthalpy of A at 50 plus 0.5 heat capacity of A times this difference, and then similar terms for enthalpy of B at 50 degrees C plus 0.5 heat capacity of B, again multiplied by 250. So we can simplify this, and we're going to do two things. We're going to combine these two heat capacity terms because otherwise they're similar. And we're going to bring this to the other side because we can see we're going to simplify. We bring this to the other side, it becomes minus HA at 50 degrees C. And we have here plus half of HA. So left side then is 0. This becomes minus 0.5 times HA at 50 degrees C. And then we're going to add enthalpy of B at 50 degrees C. And then we're going to combine these two terms, 0.5 times 250, so that's 125 heat capacity of A plus the heat capacity of B. So I've just factored out this 0.5, and then the important thing to notice, this term enthalpy of B at 50 minus enthalpy of A is just the heat of reaction at 50 degrees C. So the energy balance that might look more familiar is heat reaction at 50 degrees C and then the heat capacity term. But notice this follows directly when we start with the first law and just do an enthalpy balance, we don't have to introduce a separate term in this expression anywhere for heat of reaction for this reaction. Instead, heat of reaction drops out naturally. We do the enthalpy balance. Heat of reaction per mole, since only half a mole reacts, then the 0.5 term ends up here.